Welcome to the LemnaTec Academy. In the first video, I will talk a little about segmentation and about some basic root analysis. The second video is about a single LemnaGrid device called the skeleton interpreter. This device is essential for more advanced root analysis. The third video will present a few more special analyses you can do with roots. In the final video, I will talk about a few special points required for integrating these analyses into Lemna experiment. I will use images from rhizotrons as an example, but this analysis will apply to other settings as well. However, not all of these analysis techniques presented here will apply to all kinds of roots. Therefore, take these videos as an inspiration rather than a precise guide. I will use machine learning for segmentation. I strongly recommend this. Segmentation of root systems often depend not only on color, but on local context. The same absolute color at one point in an image might just be a piece of soil or a discoloration in the other, while the same color at a different spot may indicate root hair or an old root. These kind of contexts can be handled by machine learning better than with other segmentation techniques. I will explain how to create such machine learning models in class 6. For now, we assume this has somehow been provided to us. But now let's get into it. This video is the first of a mini-series about analyzing roots recorded with LemnaTec equipment. Originally, I planned it to be one video, but 45 minutes would be too much for a single video, so I split it into 4. I will focus in this video on the evaluation part of the analysis. Therefore, I have prepared the segmentation part already for you. Let me talk you through it quickly. First, we load an example image. This is a sunflower grown in a rhizotron. Then we apply machine learning onto it. I mentioned this device shortly in a previous video on segmentation. This device does the essential magic of segmentation. I will explain this in class 6. But quickly, on the left we have the input image, and on the right we have a color-coded segmentation result. Orange stands for root, and cyan for background and everything else. You may introduce more classes in your model, such as root hair, shoot, and assign them other colors. But this is a topic for the other video. Next, we use foreground-background separation to get the usual binary representation of the roots. Since we have a few false positives, we need to clean the segmentation. In this case, we use a fill area device with areas up to 80 pixels in size. Depending on the quality of your original segmentation, you may need a few additional steps here. I will show some of them later in this video. Now we came to the central part of root analysis. We use this binary image to create something called a skeleton. We use a skeleton extractor device for it. We find it in the feature detector group. This device converts a binary image into blue lines and red dots. Each blue line connects red dots with each other or to a terminus, or it connects to termini. These blue lines are called bones, and the red dots are called joints. Altogether, this is called a skeleton. But there's a bit more to the skeleton. At each point of the bone, it remembers the width at this point. We can make this visible with the display options of the skeleton using the bone shape visible option. These skeletons are the foundation of the root analysis. The default parameters of this device usually works well, but I invite you to play around with them to get an idea of what they do. This device has two outputs, one representing the skeleton itself, and the other is a skeleton drawn as a binary image. We can use these outputs to obtain information about the root system and individual roots. First, we can convert the binary skeleton representation into image objects and analyze them the usual way. We start by converting the skeleton into image objects. Then we merge all objects into one. Finally, we add the respective writer device. Here we can do the usual measurements of the complete root system. For instance, the convex hull or the compactness. The area in this case is a proxy for the root length, although it makes a systematic error. I will come to this in a moment. Instead of using the skeleton binary image, we can also use the original binary image. Most of the morphological parameters shall be similar or identical within the margin of error. However, the size or area now represents the visible root area rather than being a proxy for the length. On the other hand, we can use a skeleton output to create results. The simplest way is to use a skeleton list overview writer. Here we can get various information about the skeleton, like the number of bones and joints, the number of inner bones and terminal bones and isolated bones, bones in certain directions, etc. You find more about them in the device description. However, I think the most important parameter here is the sum bone length. Unlike the skeleton area we discussed before, this is a true skeleton length. Let me explain. A root which goes down exactly 100 pixels has a length of 100 pixels. But a bone which goes straight on a diagonal of exactly 45 degrees for 100 pixels has a length of 141 pixels, as good old Pythagorean proves. The area proxy we discussed before gets 100 for both of them, so it's up to 30% too small. However, most roots are a mixture of the two, even with an emphasis on the straight parts. Therefore, the error for the proxy will be significantly smaller than 30%. But the sum bone length gets it right in the first place. We can use the skeleton list writer, which will provide the same information, but for each disconnected skeleton part independently. Now let's come back to the segmentation. Depending on the quality of your original segmentation, you may have some issues with false detections, far away from the main root, and spurious side roots, where the detected roots grow suddenly a bit wider for a few pixels. See the following example. Here are a few techniques to handle these. You can use all the segmentation cleaning techniques described in previous videos, such as morphological multi-stack device and the fill area device. In any case, you should start with them. If you want to remove objects which are far away from the main root, but which are smallish, but not really small, then you can do the following. Convert the signal into objects first. Then we apply some filters on the morphology of the objects. We use the image object property filter device to achieve this. Now we need to add some filter criteria. For instance, to exclude small objects, we need a size filter. Let's say we want to keep all objects larger than 100 pixels. We select the size parameter from the filter list and add it to the active filters. We enter 100 as lower boundary and a ridiculously high number as upper bound. The objects that are kept are in green and the objects that are removed are in red. We may also add some filter based on parameters based on the shape of the objects, like eccentricity, compactness, or roundness. We can check the values of these in the input image using the tooltip to determine reasonable thresholds. Let's add eccentricity with a range from 0.5 to 1. So we have excluded two objects, this and this. Please note, objects that shall be kept must pass all of these filters. Now we convert it back to a binary image. We expand the result by, let's say, 32 pixels. These 32 pixels define the surrounding of the roots, including all small root fragments, in contrast to the regions far away of the root system itself. Finally, we combine this with the original binary image using the logical operation device with the AND operation. So, of the two objects which we have removed, one will survive because it's close by the root and the other is removed. As a result of these operations, all elements that are root-like by shape or size are kept, as well as all other objects which are close by to the big roots. The latter are likely small root fragments which belong to the root system itself. This includes also smaller roots in a distance from the main root system, as long as they are big enough and root-like enough. However, all other objects are removed. They are likely just false detections. To get rid of spurious site roots, you can do two things. Apply some multi-step morphology, which expands first and erodes back to the original form using suffix accuracy. Using 2 or 3 pixels dilation and erosion will suffice. This will smooth the edges of the detected root. Often this is already sufficient. This region is now much smoother. To check this, we feed the result into a skeleton extractor. We have less side roots here. The second option is to use the image object smoothing device. First, we have to convert the binary image into objects. This device uses a Fourier transform and cuts away all higher modes. Therefore, smaller numbers for the absolute and relative coefficient count will mean more smoothing. I suggest a value of around 20 to 25 for the relative coefficient count and select Smooth Holes. If you convert this back to a binary image, the result is less prone to spurious side roots. As a result, we are left with just one spurious side root, at least at this position in the skeleton. These are some suggestions to improve the quality of your skeletons. In this video, I demonstrated how to determine basic morphological parameters of root systems and how to take advantage of structures of roots to improve the segmentation. In the next video, we will see how to determine side roots, root angles, and other things. See you there.